welcome to the next chapter of our VELOVirtual series. This one's repeatable, reliable, and scalable, and we've also subtitled it How to Industrialize Metal AM. I'm really excited to talk about this one today. I think this is going to be a good one. This is a big theme for Velo right now, as a lot of our customers start to move from project or prototyping work into scale production. I do want to give credit for the title of this session. It actually came from a session that we were attending, Additive Manufacturing Industry Summit put on by ASME a couple of months ago. And during the keynote panel, they had a session titled Industrializing AM, Shared Challenges and Opportunities for Aerospace and Energy. And I think it was one of the panelists was Hoka Schultz from Airbus. And he was asked, what is an industrialized additive manufacturing solution? So his reply, you can probably guess, had something to do with reliable, repeatable, and upscalable. So that's where we got the title from this. So thank you to Mr. Schultz for that. You know, this was an aha moment for us. And so we kind of wrote that down, just thinking about what goes on behind the closed doors at Velo, giving you an insider peek and some of the progress we've been making. You know, we talk a lot about innovative geometries. We talk a lot about supply chain flexibility, and those subjects do bring interest from the industry, and they do start the conversations. But moving forward, especially with the customers as they evolve from project to production, the main driver for their success is the ability to leverage and to be able to provide them with the leverage for an on-demand digital supply chain. So you may have seen some PR talking about contract manufacturing partner network. That's obviously a big part of this, but we're going to dive into sort of the technical background to this a little bit more in this session. So, now, with no further ado, let me introduce our speaker. So it's an honor to introduce Will. Will, how long have we been working together? Like 2.5 years now? 2 years now?
2 years, yeah.
2 years, awesome.
Been a little while.
And we've done a lot of speaking sessions, so always great to work with Will on these types of events. Will has over 15 years of design and systems engineering and some of the coolest technologies on the planet: jet engines, race cars, additive manufacturing. So pretty awesome work there. Prior to being an engineer, he was operating nuclear power plants for the US Navy. So thanks for your service there. Another really cool application. Will holds a BS in Aerospace Engineering from Embry-Riddle Aeronautics University and an MS in Mechanical Engineering from the University of Cincinnati. With over 18 patents, he is a registered professional engineer in the state of Ohio and is fluent in both English and French. And we've definitely done a couple calls where I've seen that French talent. So Will, I'm going to turn it over to you.
Outstanding. Thanks for the intro, Mike. All right, so today we're going to talk about realizing a dream. And the dream is having a series of metal AM printers distributed throughout the world in local regions. And then you can take a part file and you can send the part file to whichever printer is closest to where the demand signal is. And you basically have that part printed locally on the printer, and you get the part where you need it and when you need it. However, when we're looking at the conventional AM systems out there, there's really some difficulties that are encountered when trying to scale technologies that were really meant for the prototyping industry or printing parts in a lab, and you're trying to really scale it on a global scale. So if we look at the workflow here, you first start off generally with conventional metal AM systems with a CAD file. It then has to be converted to an STL file. You then pull in the STL files into your print preparation software. You have to fix translation issues oftentimes with STLs, flip triangles, etc. And then after the build file is prepared, you then have to slice the build file. And at this point, you need to know which printer serial number you're going to be printing it on. And you also need to know what's the calibration state of that specific printer, because the print file oftentimes is used to take out the slop or the variation in the optics for each printer. And so this creates a very cumbersome situation. For instance, you have a lot of files that you have to track if you're in a highly regulated industry. Additionally, if a technician goes home over the weekend or say takes a few days off during his time off, the field service engineer comes out and calibrates the optics on one of these systems. He comes back, he can't use that print file from last week because he'll then be printing faulty parts on an uncalibrated system if the laser has been recalibrated during his time off. So this can create a lot of confusion, very precarious situation just when you reach serial production with this. Additionally, you'll notice that there's 3 months between calibrations in this example. 3 to 6 months is common. And the problem with that is it opens up a door of creating a lot of parts at risk, parts that can be printed on uncalibrated systems. So that's a lot of risk brought to the supply chain. And then finally, there's a lot of variation in these systems. And we're going to talk a lot today about printer to printer variation as well as variation throughout the build. And with these legacy systems, not only is there a lot of builds that have to be done to qualify the printer, also each part has to be qualified on that printer oftentimes as well, just to characterize the variation of the unstable process. So at the end of the day, this creates a situation where it's precarious to roll out just across the site. When you start looking at this on a worldwide level, it really becomes an impossible task. So next, we take a step back to think, okay, how do we crack the code on reliable and scalable metal AM? And Velo3D's solution to this is really creating a full stack solution. So here you have our 3 main products: the Flow print preparation software, the Sapphire family of printers, and the Assure quality validation software. And this is really a process flow here across from left to right on the screen. So you can see a CAD, the native CAD file is pulled into the Flow software. This is where supports are added, process overrides, a Velo build file is created, and then a Velo print file is created after the part is sliced. And this Velo print file is able to be used on any Sapphire printer worldwide. And then, once it's time to print on that Sapphire, the Sapphire is calibrated. We'll talk about these calibrations today. And then finally, in the Assure quality validation software, we have 970 different sensors that are logging real-time data. And we're basically looking through that and logging it and monitoring it in Assure and giving unprecedented insight into the build process throughout the build. So the 3 key pieces of the puzzle that we'll be talking about is, first off, having a series of qualification builds and weekly calibrations to make sure the tools are healthy and you have consistency across the fleet of Sapphires. Secondly, we'll be talking a lot about Velo print files. And the reason we will be is because this is about driving part traceability through having a single print file versus a series of print files. And really the reason this is so critical is having the same laser instructions always being sent to the printer to have the exact same part printed. And then finally, having one system of record for part print files for all sites. And this is really the scalability aspect to it. So not just having a consistency in your factory at one site, it's about having a distributed supply chain that you can leverage. So first off, to talk about machine qualification, this is just a high level before we dive into the details. So there's a variety of qualification builds that we'll be discussing. The first is a site acceptance test. This is really a Velo3D generated build file to determine the tool is healthy and operating within spec. Next, we have the Sapphire qualification build. So this is an OEM derived build where basically there's oftentimes a material database that already exists, and it basically buys the Sapphire, specific Sapphire serial number into that existing material database. And then finally, there's a part qualification build. And this is the actual Velo print file that's used in production. And this is basically analogous to a first article inspection that is common with standard conventionally produced parts as well. And then underneath it all, what's tying it all together is making sure that we don't have consistency, or ensuring that we have consistency in avoiding variation across the fleet. And so through this, we have optical calibrations, thermal sensor calibrations, and powder bed quality verified weekly across the entire fleet of Sapphires. Now, looking here at the site acceptance test, so this is this right here on the right side of the screen, you can see this is our site acceptance test build, and coincidentally, it's also the factory acceptance test build. So we have this build that we run before every Sapphire leaves the factory, as well as when it's installed at its final location. And so if we look here, there's a variety of aspects that we're validating. So first off, dimensional accuracy around the perimeter of the build plate is being verified here. Next, we have a process tree in the middle of the build plate. This is being made with both lasers at a variety of angles and basically pushing the processes to their limit because it's at the limit of a process that you see variation, if variation is going to occur. Next, you have tensile properties, so you can see as printed and as machined tensile bars for each laser. Material density or lack of porosity is also verified. And then finally, surface finish is verified on several parts scattered around the build plate. This is basically the geometries that the VELO3D process engineering team has deemed as the most challenging to ensure that that the tool is operating well within spec, even at some more challenging geometries. So once the site acceptance test is complete, the customer signs off that, in fact, the results are satisfactory as well. We have a report out to the customer there. And then finally, we move to the Sapphire qualification build. So this is the OEM-derived build that it really varies for us customer to customer, because we have, some customers are designing jet engines, rocket engines, turbo machinery, all sorts of variety of applications. And different applications have different design requirements. And because of that, different material properties are being validated in these builds. So that's what drives the variation from OEM to OEM. Typically, these are a mix of laser 1, laser 2, and dual laser specimens. And just have a list here of what we commonly see with these. So tensile properties are basically always there. Oftentimes, designs are limited by fatigue. And so fatigue is often verified. Toughness comes up as well. And then generally, there's always a process cube in there for verifying the lack of porosity in the microstructure, chemistry, surface finish, and dimensional accuracy. This is a little redundant with the site acceptance test build, but many OEMs want to just have that level of consistency where they're tracking it on their Sapphire machine or Sapphire qualification build reports as well. So now we'll talk a little bit about laser power bed fusion sources of variation. So there's a variety of problems that are common in the industry with other systems, and that drives a lot of rigor and extra builds that are in order to characterize a process that isn't necessarily stable. And the first step in qualifying a process is making sure that the process is stable, because processes that are stable are easier to characterize and qualify. So the first two are variations in the X and Y direction or across the build plane. And then the last two are variations in the vertical direction or the Z direction. So first off, in the X direction, X and Y direction, we have gas flow inconsistencies. Dead zones are a common problem. We have consistent gas flow across our chamber. We don't have any obstructions like recoders in the way, etc. Additionally, laser incidence angle can cause variation across the build plate. And for the VELO3D processes, they're qualified and developed not only directly underneath the laser, but also at the extremities of the build plate, so that day in, day out, you don't see that variation with respect to location. Next, there's so commonly there's build plate heating or powder bed pre-sintering or build chamber heating that occurs in other systems. And this can cause variation in the Z direction with material properties. You get larger grains towards the bottom, smaller towards the top. At Velo3D though, with our Sapphire, there's no heated build plates. There's no preheating of powder. We do this in order to drive uniformity throughout the build volume. And then also another common problem is if you're working with heavier alloys such as Inconel 718, you can have frame flexing as a function of the powder hopper level. So when the machine is full of powder, the frame flexes down and the laser spot can move. And then if you refill the powder hopper, then it moves again. And so this makes it very challenging to characterize. However, if we look at the Velo3D Sapphire, there's no load path between the powder hoppers and the main frame. And so there's no, it's not a stressed member. So because of that, we don't encounter this problem either. So, that previous slide was more about overall machine design, printer design. But then there's other sources of variation that we basically work to calibrate each Sapphire to. And all of these calibrations that we're about to talk about, these are all done with the push of a button with a technician, by a technician who is actually operating the Sapphire day in, day out, not a field service engineer. So the first one is beam stability. This is basically verifying that the optical train is clean, and when if there exists an optical train, then the spot will move as the optical train heats up. The debris will heat up and cause variation with respect to time and temperature. So we verify for that with beam stability. Next, we have spot diameter or laser focus. So we're basically verifying the spot diameter does not change as a function of location on the build plane. So we're verifying the spot diameter at 49 different locations across the build plane. Next, we have laser alignment. So we're doing laser distortion mapping on each galvo. And then we also map the two lasers to each other at 500 different points across the build plane and basically ensure that the laser spots are coincident with each other. Next, we calibrate the thermal sensor offset to ensure that we're getting a strong heat signal or thermal signal from the melt pool. And then finally, we have some really unique capabilities relative to the powder bed verification. So first off, we have a 3D topographical map of the powder bed that oftentimes we call height mapper. We can use this to basically verify powder bed flatness. So this makes sure that you have a consistent layer of powder across the powder bed, and which is important because basically the powder is your feedstock in a welding process. So you need to make sure you have a consistent amount of feedstock as you're welding. And then also we're able to look for erosion events. So erosion events can occur if there's a problem with the gas flow where it's basically eroding away the powder bed. So we verify for that as well. So all of these calibrations together, these are done weekly by a technician, as I was saying, and we find them key to ensuring that there's not variations in the build across Sapphires. So now I'd like to show you a couple different plots because we just talked about consistency and in and out. And you see right here, this is consistency across the build plate in X and Y direction. These are Type 64 ELI bars that were tested. We have ultimate tensile strength, yield strength, and elongation. And we're basically seeing, there's a very tight distribution for each of these. And maybe just to explain the plot just a little bit more to make sure everyone understands what we're looking at. I'll talk us through the UTS here. So this is the Y direction of the build plate. This is the X direction of the build plate. We have a 315 millimeter diameter build plate. So that's what these dimensions that you're seeing here on each plot. When you look at these, really a couple of key things. First, all of the values are well above the spec minimum. In this case, ASTM F3001. Additionally, you can see there's really no clear trends of variation across the build plate. And we're also getting a very nice tight distribution across the plots. So very high values, tight distribution, and you're not seeing any trends. Additionally, looking at the variation in the z-axis. So we get a lot of questions about whether it's variation due to height in the build volume or also free floating or non-free floating parts. So free floating parts are not connected to the build plate. This is a unique capability that Velo3D has to use our non-contact recoders. So basically what we're doing with the plots here is we're verifying, you can see here on the left side of the screen, a layer of attached bars to the build plate, a layer of free floating bars above that, and then also laser 1, laser 2, and dual laser bars. Dark blue is the attached and first layer. The light blue is the free floating or the second layer. And you can see consistency both in the average and the -3 sigma properties between these two different data sets. So now we'll take a look at part qualification, because now we've talked through having a consistent fleet of Sapphires worldwide, but the next aspect is ensuring that the part itself is meeting requirements. So with the part qualification build, this is basically verifying that all the processes working in tandem are working together correctly. So at this point, we're working with the actual Velo print file that will be used in production throughout the production life of the part. So and really at the end of the day, this is basically a first article print. So with that, similar to other with standard first articles for conventionally made parts, you have dimensional accuracy, surface finish, and cut-ups as well to verify lack of porosity. So cut-ups are common as well first time you have a forging or a casting, and it's similar here. Additionally, with each part, generally there's 2 tensile bars, a process cube, and a powder sample that is taken at the same time just to verify quality of build that are added on. And so bear with me here as we talk a little bit more about the details of the flow preprint software, and we'll talk more about the Velo print file and the significance of what's going on here, because it's really locking down the directions of how that part is produced. So first off, we have with flow 2 different portions of flow. The first is the build preparation portion, and the next is the process review portion. So with flow build preparation, with the build prep, basically the CAD file is pulled in, the part is oriented and then supported. We then apply process overrides. So process overrides is, say, for instance, if you want no contour passes to occur on a certain surface, that would that's where those directions are applied by the user or manufacturing engineer. And then the build plate is populated. So you do this for one part, and say you want to produce 10 parts on a build plate, you then array them around on the build plate. Next, the file is the Velo build file is sliced. And as slicing occurs, it's basically taking the geometry and slicing it into 2D sections. And then if we look over on the right side of the screen here, you can see a variety of different parameter sets. So we have over 24 different parameter sets per material at Velo3D, a very extensive library. And you can see right here, for instance, you have a bulk parameter, you have vertical walls, lattice, low angle walls. And really what is occurring is based on the geometry, it's a different thermal environment and a different thermal input that needs to be applied to that specific geometry. So the flow software is taking a very sophisticated look at the geometry, and basically as it cuts up or slices the geometry, it's determining which of these process sets needs to be applied for each specific location on the part. And then from there, the laser instructions are generated, and then the VELOprint file is created. The VELOprint file is then opened up in the process review, and the manufacturing engineer will review the prepared file, the prepared print file, just as a final verification before it's sent out to the printer, just to make sure that processes were applied. There is no obvious issues with how the part sliced. So now if we look back to back of the conventional or other metal AM systems versus Velo3D and this workflow here, you can see it's greatly simplified. You have a multitude of files on the top. On the bottom with Velo3D, you basically have your CAD file that's already been created. You then bypass having any STLs to track. You then have the Velo build file that's created. And then regardless of printer serial number, regardless of which calibration has occurred to the optics, you have one single VELOprint file for all Sapphires worldwide. So from a part traceability standpoint, this is a night and day difference. And so I'd like to talk a little bit more about the significance of this, because now that we've locked down all of the laser parameters into one file, it's important to validate that file. And it really is the process mimics that of the first article inspection kind of methods that already exist with conventionally manufactured and conventionally designed parts today. So there's three different types of defects that we find in first article inspections. First is surface defects. So these are visual to the eye. A couple of different drivers here. Perhaps, it's the geometry is too low of an angle. So we've just, been too aggressive. A lot of times we have customers, they love having far fewer supports than other systems out there. And sometimes they get a little overambitious. But no worries there. You can basically, if this occurs, you can either adjust the angle in the design or else add some supports or apply different processes to overcome these issues. Next, low angles can be more challenging when you're farther away from the laser. So while we develop our processes to work throughout the build plate or across the build plate, still you can come across some extreme cases where you start to see laser normal effects at the extremities of the build plate. And then additionally, geometric deformations. So unconstrained geometry, or you have high residual stresses. Sometimes if you have a thin tube with a very large lug at the top of it, you're going to see some deformation there, things of that nature. And then also with large diameter parts, there will be some thermal shrinkage that occurs. So that's another thing to keep an eye out for. And then finally, lack of fusion porosity. So we've come across this a couple times in first article inspections. The first one is we had a case where we had a layer of lack of fusion defects that occurred due to incorrectly applied processes. It was consistent. There was, of the 10 parts in the build, they were cut up and they consistently had the exact same lack of fusion porosity on the exact same layer. When we looked at it further, it was incorrectly applied process. We fixed that in the Velo build file, resliced the file, reprinted it, cut it up, and the lack of fusion porosity was gone. The other one was last year we had an issue where it was basically a perfect storm that occurred, where a bunch of compounding aggravators in a build created a lack of fusion defect at a very specific location. And as we worked to remedy this problem, we reproduced the exact same pour on 20 different parts, 20 different builds, I should say, 20 different unique builds across 4 different alloys. And it was tremendously aggravating to have that many attempts to address a problem, but we finally fixed it. And the reason I like to bring this up is because when you're consistently creating the same problem in a controlled environment, that means you can have a repeatable solution. So at the end of the day, our process engineering and software engineering teams developed a solution. It made us stronger. We've rolled out improvements in our processes as well as software because of this obscure corner case to make sure that not only doesn't happen on that part, but it doesn't happen on when similar situations occur going forward. And now that's finally fixed, the parts that now that part is being when that part is produced, then the lack of fusion defect no longer is occurring. And really to drive the point home, this is why our customers continue to take this first article inspection approach. The very nice thing about working with Velo3D's ecosystem is when a defect occurs, it's repeatable. And so when you have the fix, it's repeatable as well. And it's a night and day difference when you're chasing your tail with part to part or build to build variation. It's a breath of fresh air. So now we'll talk about fulfilling the dream of a scalable AM solution. And this is a bit of a tactical slide, but there's most companies out there are now using PLM software as they control the configurations of their products. This is where the CAD files are locked down, the drawing files are locked down, and it's basically a single source of truth or a system of record worldwide. And so what occurs here, if we just kind of look through the steps of going from concept or inception of the design to the part being printed, you first have in the CAD software, the design engineer will release the design and lock down the model. And that's uploaded into the PLM system. From there, the manufacturing engineer pulls down the part file. He then loads into Flow, creates the Velo build file after preparing the model. The manufacturing engineer will then slice the file and create a Velo print file. He'll verify that the Velo print file looks acceptable, and then lock down both the Velo print file and the Velo build file and upload those onto the PLM system. So if you see a common tree for a part number right here, the 333-265 P01 will say, you can see there's a part file. This is a CAD file. You have a drawing file that's on Rev 2, and then you have Rev 1 of the build file, Velo build file, and Rev 1 of the Velo print file. And this is tremendously powerful because now anyone who has access to that PLM system can basically pull down that Velo print file onto the Sapphire and then start printing that part. So really a night and day difference from the transferring files around with USB drives and etc. So now talking about a couple of cases of how this is being implemented in the field. With OEMs, certain OEMs, they are bringing in Sapphire in-house. They qualify the part in-house. This is where they create the Velo print file. But with as they grow and as the part is going from concept or prototype to, or I should say, development engines, development builds to full-blown serial production, instead of just printing the parts in-house, they're actually sending the Velo print file to multiple contract manufacturers or suppliers across the world. And so this brings a very nice and consistent part product or very consistent product back to them. They always get the exact same file. This is a night and day difference from sending a CAD file to a contract manufacturer who doesn't really want you to know how they support the part. There can be variations in orientation, all sorts of other things that would that need to be validated. And for flight hardware is just too difficult to substantiate or unsatisfactory. So having this single Velo print file is tremendously powerful to drive consistency across your supply chain to make sure the part that you're printing in-house is also the same part as what you're ordering from a contract manufacturer. And so just to finally close the loop on this, with the distributed supply chain, how this works is you basically have, if you are, say, one single company or entity, you can then deploy Sapphires throughout the world where you need them in the region where the parts are needed. And then pending that all the different Sapphires have access to the same PLM system, then the order is sent to the specific factory and region. They then pull down that specific Velo print file, load it onto their printer, they print the part, and you have this worldwide consistency. It's like the McDonald's model where the Big Mac in St. Louis is supposed to be the same Big Mac that you get in Budapest. So anyway, it's a tremendously powerful concept, and it's not just theoretical. This is what we're seeing occurring today across our customer base, and really exciting advancement for Metal AM as we shift from prototypes to serial production. So in summary, worldwide scalable AM is not a dream. It's occurring today. It's made possible through a series of site acceptance tests, Sapphire quals, part quals, and really having this continuous, continuous calibrations that occur on a weekly basis. So really locking down the process, and that's what's driving this consistent part production. The reason this is made possible as well is really our full stack solution at Velo 3D that drives the single print file concept. And then finally, these principles, they're heavily being influenced by the aerospace industry because the aviation and space industries are early movers in additive, but really this applies to any industry where quality parts are necessary and required. And so the principles here are heavily influenced, but really going forward, we expect this to be applied to any industry that's embracing Metal AM for production. So with that, thanks for your attention. I'd like to now open it up for questions in the audience. All right, I can't hear you, Mike.
Oh, there we go. It helps to have two mute buttons that you have to hit it twice. Yeah, so we are going to open it up for questions. And just to kind of reiterate, we'll be monitoring the Q&A panel, not the chat panel. So if I did see a question come in through the chat panel, if you could just copy it over into the Q&A, we'll run through that. So, all right, a couple here. Thank you for the interesting webinar. So good job. The qualification standard shows the qualification process shows a very high standard. How much time does the process take, especially when testing in the Z direction?
Z direction build it varies with the height. I mean, and how many bars it can be, say, a 5 to 7 day build for a full height Z direction build. So because of this, we recommend, based on experience, not necessarily doing full height Sapphire qualification builds on a repetitive basis, but using the data that does come off when you do full height builds and using that to substantiate doing shorter qualification builds. going forward so that you aren't using so much time and resources for just printing bars that are at the top of the build chamber. So, you know, generally 5 to 7 days, but really as time goes on, we're seeing a shift to doing shorter builds. Even our site acceptance test builds used to be full height. And then when we saw the data and lack of variation, it seemed like a waste of resources to continue doing those long builds for no reason. Good question.
There's another question here about qualifying new materials. Could you maybe walk through Velo3D's process to qualify new materials?
Yeah, absolutely. So for new materials, so our parameters are, we develop our parameters in-house. So we have a variety of materials today, Inco 718, Inco 625, Ti64, Hastelloy X, F357, aluminum, and then we're also bringing on Scalable here shortly. If you need a different material and you have a production need, we will develop that as part of the agreement for the purchase of the printer. That's not an extra cost that's passed along to you. We'll work with you based on your requirements and in order to develop the material to your satisfaction.
There's slide 15. I think that was the one where you showed the tensile bar distribution.
Sure.
Right, this one. So this one's a new one for me too. So the comment was, if the build plate is circular, why do the graphs look more like polygons than circles?
So this is these are jump plots, and so it's just a function of the location of the tensile bars and the specific XY coordinates.
And maybe there was a question here about how close we are to the specification minimum, specifically to yield strength. I noticed you have that labeled here as less than 795. And for some people, I know the colors on monitors might vary. Maybe you could talk through where these bands are on this graph over here. Does that make sense?
Yes, absolutely. So if we look at the yield strength, the lowest is in the 815 to 825 megapascal range, where the spec is 795 megapascals. Similarly, on ultimate tensile strength, we're in the 980 to above 1010 megapascals, where 860 is the spec minimum. And then similarly, you can see 10% is the spec min on elongation, where we're in the 17% and above. It's really 17 to 24% elongation. So good questions. It's always challenging to present data in a public forum in a way that makes sense instantaneously. So no worries on the questions. Are there any more on this slide, Mike, or should I?
Those are the two.
Move back. Okay.
Yeah, I do have a couple questions on flow. The first, can you use flow for other printers? Meaning other other manufacturing, other printers from other manufacturers.
Yeah, so it's really important to use. First off, no. Flow works with the Sapphire, and the Sapphire only works with flow. And the reason that is because there has to be this continuous, throughout the development, we've had this continuous feedback loop of the print results on the printer is what drives, whether it's machine upgrades, hardware upgrades, software upgrades, or process upgrades. It's really an ecosystem, and you can't separate the software from the hardware and vice versa. And that's really also enabled us, we're well known for being able to print crazy geometries. And the reason we're able to do that is because of having the software and hardware integration. So we don't have that barrier between the software and hardware that other systems out there have.
And regarding flow, or maybe in the VeloPrint file itself, does it allow for serialization or marking?
So that's something we've been requested and we're working on still. Right now, a lot of the marking occurs on the CAD file side, but certainly that's something under development.
There are a couple questions here with regard to the PLM. You showed kind of a network going to different places on the globe. There were some questions around security of the PLM system. And so maybe, can you walk us sort of through what that slide mean, what's the context around that slide maybe?
Yeah, so with the PLM, there's software. So I'm not an IT guy. But basically it's, having a single network where all the different organizations in a company can reference this common software platform. So to be clear, the intention here with the PLM, we haven't mentioned any specific names for the PLM software. The idea though is that basically, anyone designing products out there has a PLM system where it's a single resource for their CAD files and their drawing files. And what the nice thing is with Velo3D's single build file and single print file, it can basically leverage this existing system, your existing ecosystem for configuration control, and not having another add-on piece of software to track your build files and print files on top of the other system. So it basically just, we can fit right in homogenously with the system we already have in-house today.
Yeah, so we're not providing this network, and the security is kind of up to the customer.
Correct.
Yeah. Now, there were some questions about different powder suppliers with regard to this network, and like how sensitive is the Velo3D solution to different powder suppliers?
So we're powder agnostic. So the contract manufacturer or OEM who purchases the system, they determine which powder is loaded. So from there, when the Sapphire is on the factory floor at Velo3D, we load it with that powder. We do the factory acceptance tests with that powder, and then that's what's loaded again when it arrives at the facility for the site acceptance test as well. So it's customer driven. And what I think I might have already said this, but we are powder agnostic, so we do not sell powders.
And so with there was a question here about the VeloPrint file. When you send that out, and is this the exact same processing conditions for each of these printers in that case? And how do you ensure that all the printers are going to behave the same, given the same instructions?
Yeah. So the reason the printers that we specifically have created the site acceptance test build and machine calibration routines, basically to verify that the Sapphires themselves are performing consistently across the fleet. And then additionally, from the OEM side, they have their additional qualification builds that they overlay on top of that in order to have yet another level of verification that the Sapphires are working correctly across the fleet.
Is there any restriction in terms of the powder shape, like gas or plasma atomized, or particle distribution size, I guess, as well?
Yeah, so we've run both gas and plasma atomized powder. There's no issues there. There's certainly flowability is key. And also with particle size distribution, we use standard particle size distributions for Inconel 718, for instance, 1545 PSD. You generally want to stick with that. If you don't, then you can have some sieve problems where you're throwing out good powder, sieving out good powder. And then additionally, with the lighter alloys such as titanium or aluminum, you slightly have a little bit larger PSD, say like 2063 PSD or things of that nature. And that's common just because the flowability has an inverse relationship with the density of the material. So you want to make sure it flows well and consistently.
Okay. Does the printer or does the Velo solution provide any kind of qualification for the part that was printed? Any kind of reports for that happened after the
absolutely. So with Assure, so we have a whole other presentation on Assure that in and of itself is another probably 40 minutes. But part of that, what's covered in that is all of the different quality validation or the quality validation software. So we have control charts, heat maps, 3D images of or basically topographical images of the powder bed, all sorts of other aspects that's going on from the part verification side of things as well, in conjunction with this. Just for brevity, we had to keep the subject a little focused here to get through.
Yeah, I would say that there are a lot of questions on post-processing. We just finished a webinar at the end of March with Duncan Machine Products, one of our contract manufacturing network partners, and we dive into all of the post-processing and kind of pre-processing that goes into a single part. So if you have any questions around that, please check out that webinar. And I'll just answer probably 4 or 5 of these with the it depends. For any of your post-processing, that's kind of the easiest answer. Is it's going to depend on what the requirements are for the part. But definitely check that out and see what the time is involved for each of the steps. We walk through it in that session as well. It's another like 35-minute discussion. All right. Do we have any design guides?
Yes, so we have the Velo 3D design guides. We have a series of YouTube videos as well where we discuss these. But yeah, because we don't run into the recoder clash issues because we have a non-contact recoder, as well as we're able to print at much lower angles than 45 degrees, generally down to 0 to 10 degrees based on the geometry. There's the residual stress and the structure stability plays a greater role. So we have several plots out there of minimum angle as a function of geometry shape. And that helps design engineers and manufacturing engineers alike to really get the optimal solution from Velo 3D's technology.
We have a couple questions here. Do we have any partners in Europe? We do. We have a company called CRP Mechanica, who is a distributor of Velo 3D Sapphires in Europe. They can also give you some information if you're interested in parts. And we have a partner, Excelencia, who works out of Spain. So either one of those companies, if you want to talk to them, you can talk to them about your part applications, or if you're interested in a Sapphire printer. And I will send out a couple links in the follow-on here. One with the Duncan Machine Products webinar that we just talked about. I did see a note on that. And then a couple other ones as well. The Innovator's Guide to Metal AM, we have a webinar on that. So I'll make sure to include that one in the follow-up so that you can get that information. I guess the last question, any closing thoughts in terms of the content? I think we're kind of up on the hour right now, so we'll wrap it up with that.
I'd just like to say, thanks for everyone who joined the session today. This is a really exciting point in Metal AM as we're shifting from prototypes to production. Many parts out there are already flying, and it's going to only increase with time. And really nailing down this qualification, these qualification aspects is key to making sure the industry and the technology continues to impact lives and not just stay in a lab. So thanks again for your time today.